Math 1, Practice 2.5.2, Graphing Exponential Functions. Okay, now a few things to talk about exponential. Typically the equation is a times b to the x. That a is your y-intercept, the b is what you're multiplying by, the growth. Okay, it could have a plus or a minus a number out here, which is going to shift to up or down. Okay, and let me show you what I mean. So, here's some two just regular ones without the pluses or the minuses. Okay, so notice with exponentials we have what is called the asymptote. Basically it's an invisible line because of the nature of multiplying, repeated multiplication or repeated division. You never get below something. So this x-axis, actually, even though it looks like they'll touch, our graphs will keep going and never actually hit. They'll get super close, but they'll never actually hit it. Okay, so the number in front, y-intercept, kind of, shows you where it's crossing the y-axis, and then the numbers in the parentheses are showing you what you're multiplying by. Okay, this purple one, if you multiply by a fraction like that, it's going to be a decay. If you multiply by a regular number, it'll be a growth one. Okay, so that's what they mean on these first ones when they're saying describe the end behavior. They want to know basically where's the asymptote. Okay, now notice we have some numbers here. Okay, y-intercept should be easy to identify on all of these. Okay, it's not the number in the parentheses, it's the number right in front. So the y-intercept would be 0, 3. The y-intercept 0, 5. Okay, the y-intercept 0, 4. You get the idea? The y-intercept 0, 7. The y-intercept 2, not 2, 0, 2. Could these have some x-intercepts? Yeah, but we're only concerned about the y-intercept. Y-intercept 0, 1/4. Okay, now what about these other things? So I graphed them to kind of show you how that end behavior is going to affect them. Okay, so if we look at these ones with pluses, remember 0 was where the normal y asymptote was, but now they've been shifted up, haven't they? The green one has a +2. Okay, +2, but it's also got that 7 right there, doesn't it? So 7 plus 2 gave us 9. That's why the y-intercept got shifted up to 9, and I guess I needed to take that into account, so I kind of just did all those ones wrong, didn't I? That's what they would be without those, but then you would add it, 3 plus 4. Because to find the y-intercept would be to have the 0. Okay? 3 to the 0, or 2 to the 0 is 1, 1 times 3 is 3, plus 4 would give us 7. So I was erroneous in that. I forget about the pluses and the minuses sometimes, so I apologize. That's what they would be if we didn't have this plus, or this minus, or this plus. Because of that, you're going to have to add. So 5 minus 4 would give us 1. 4 minus 6, negative 2. 7 plus 2 would be 9. 2 minus 3 would give us negative 1. And 1/4 plus 1 would be 1 1/4, or 1.25. So now hopefully that helps with the y-intercepts. But now take a look at the, so we had 3 plus 4 for the black one, that gave us a y-intercept of 7. 7 plus 2, y-intercept of 9, 1 plus 1/4, 1.25. Now normally the asymptote runs across the x-axis, but look what happens. So we added 4, okay, and we go up 1, 2, 3, 4. Does that look like where that black one is? Yeah. So that plus 4 affected our asymptote. It shifted it up 4. Okay? The way you'd write that is the asymptote is y equals 4. It's a horizontal line. Okay, now if we look at the green line, okay, look where it looks like it's at 2. So we went 1, 2. We shifted it up 2, so it would be y equals 2. Okay? Then for our last one here, it was plus 1, so we shifted up to y equals 1. So that number at the end affects our y-intercept and our asymptotes. Okay? So for this one, y would equal 4. That's our end behavior. Okay? Then y equals 2. Then y equals 1 for our asymptotes. Okay? We got that? Now let's see if it works for the negatives. Does it work the same way? Okay. Well, we'd have a -4 for the red, so we should go down 1, 2, 3, 4. That looks like that's its asymptote, so y equals 4. Our y-intercept would be 5 minus 4, which was positive 1, so that's true too. Okay, for our blue one, -6, so we should go down, and I cut it off, but here at -6, you'd have your asymptote, so y equals -6, and so our last one, -3. Okay, purple, that's where our asymptote is, so y would equal -3. Okay, so looking at the equation, you can see that end behavior because of where those asymptotes are, and the number in front, and if we add or subtract effects, where our y-intercept is. Okay, and if you know that pattern, then it should be fairly easy to deal with all of these, given these functions. And if you have to graph them, just use technology to get them graphed. Okay, no sense beating around the bush on that. Alright, now let's look at 7. A certain radioactive isotope has a half-life of 6 hours, so every 6 hours it's cut in half. The starting amount is 100 grams. Write an exponential function to model this scenario. How much of the isotope remains after 12 hours? So, the way to think about this is we go f of x equals, where's our y-intercept? Where did we start? We started at 100. Okay, what are we doing? It's a half-life, so we're timesing by 1/2 every how many hours? 6 hours. So I'd go x divided by 6. Okay, then how much is it going to remain after 12 hours? Well, we just plug 12 in for that. Okay, could I graph it and then use that to find it? Yeah, I could, but let's just use this. So we'd go f of 12 equals 100 times 1/2 times 12 divided by 6. 12 divided by 6 would be 2, right? Okay. 1/2 times 2, that's like 1/2 times 1/2. So 1 times 1 is 1, 2 times 2 is 4. So we get 100 times 1/4. Timesing by 1/4 is the same as dividing by 4. So in 12 hours we would have 25. Because, think about it, after the first 6 hours, it'd be cut in half to 50 grams. After the second, it would be cut to in half again to 25. Okay? Alright, number 8. You are growing bacteria for a science experiment. The number of organisms triples, times by 3, every 10 hours. You begin the experiment with 20 organisms. Write an exponential function. How many organisms will you have? So f of x equals, we started with 20, we're timesing them, tripling them by 3 every 10 hours, so x divided by 10. How many will we have after 30 hours? Well, 30 hours is 3 sets of 10, right? Because 30 divided by 10 would give you 3. So f of 30 would equal 20 times 3 cubed, right? Because we already kind of simplified that. 3 cubed is 3 times 3 times 3. 3 times 3 is 9. Times by 3, one more, is 27. 20 times 27 would give us 540. So after 30 hours, we'd have 540, which makes sense. Okay, at 0 hours, we'd have 20. After our first set of 10 hours, we would end up tripling it, 60. After our second set of 10 hours, triple that, 180. After our third set, triple that, 540. Okay. Now, could we take this and graph it? Yeah, or use graphing technology. By all means, do that, and then look where the x is 30. You've just got to remember that thing. If it's like every 10 hours or every certain amount of hours, you've got to remember that part of it. Okay. So number 9. Violet invests $400 in an account that earns 2.5% interest per year. Write an exponential function to represent this scenario. Okay, so every year, so we start out f of x equals 400 in the account, timesing by, not by 2.5, because remember, you take 100%, because we're not losing money, and you add 2.5% to that each year. So it'd really be 102.5%, but we change it to a decimal, so it'd be 1.025, okay, and that's every year. So how much would we have after 7 years? So f of 7 would equal 400 times 1.025 to the 7th, which this I would just type into a calculator because 1.025 to the 7th is like 1.188685575. You know, it's crazy. So just type it in as a calculator, and we get, now we're dealing with money, so we need to round to the nearest hundredth, $475.47. Okay, and there we go. Alright, number 10, last one here. So the graph of a function is shown below. Write a scenario that could be represented by the graph. So what we need to understand is our pieces, right? So what's our y-intercept? Would be 15. How is this growing? Well, 15, and then it goes up to 35. Notice that it goes down. We're subtracting 5. So I'm going to have a minus 5 back here, aren't I? Okay, and that's going to affect things because everything is going to be shifted by that. So if I look at a table here, we start out at 15. Okay, then after the first, we're up to 35. After the second, we're up to 75. After the third, we don't know, do we? So what are we multiplying by here? Okay, well, what if we were to subtract 5? Okay, because we have to deal with that 5, don't we? Let's see if going backwards any further helps us. -1 and -2. -1 would be at 5, and -2 would be at 0. Okay? So the way to think about this is what if this 5, if we weren't shifted down 5? What if we added 5 to everything? So if we add 5 to everything, that'd be 5, 10, 20, 40, and 80. Now we can see a pattern, can't we? 5 to 10 to 20 to 40, we're times them by 2 each time, aren't we? But because of that 5, it kind of threw us off. So times 2 to the x, and then we'd have that minus 5 at the end. Okay, so what's something that we started out at 15, and you're doubling, okay, and then we started out with less 5, okay? Alright, so that's the scenario you're looking at. Usually some sort of population growth, whether bacteria or something like that, is the best route to go. I'll let you do the rest of that, and there we go.